Hi everyone, this is Midhu T. Augustine and welcome to the lecture series on linear quadratic regulator or LQR. LQR is an optimal control approach which uses a linear model of the system and the control input is computed by minimizing a quadratic performance measure. In this lecture series, we will be discussing the different formulations of LQR such as continuous LQR, discrete LQR, constraint LQR along with its derivations and numerical implementation. In this first lecture, we give a brief introduction to the LQR and its different formulations. Here is the overview. We start with the introduction and state space representation of linear system with examples. Then we move on to the LQR and its different formulations. Optimal control is one of the modern control approaches that integrates optimization to controller design. In optimal control, the control input or the control law is designed for minimizing a performance measure of the system, which we also call as the cost function. And the control design problem can be formulated as an optimization problem. Linear quadratic regulator or LQR is one of the most popular optimal control approach. And as the name implies, the key features of the LQR are: it uses a linear model of the system for controller design. The performance measure used in LQR is quadratic. And LQR is used for regulator application, in which the objective is to regulate the system state at some operating point. Figure 1 shows the general block diagram of a dynamical system with an LQR controller. A mathematical model which describes the dynamics of the system is assumed to be known, and for LQR controller design, we use a linear model of the system. The LQR can be designed based on either output feedback or state feedback, but it is usually considered as a state feedback based approach. The desired operating point where the output or state of the system is needed to be regulated is specified by the reference, which is usually considered to be 0. However, we can also have non-zero reference points with the LQR. LQR uses the reference, feedback and system model information for computing the control input. And in LQR, the control input will be a linear state feedback with an optimal feedback gain. The notations used in this lecture series are standard. We use normal font for representing scalars, bold font for representing matrices and vectors, and blackboard bold font for representing sets. Next, we move on to the different Shapespace representations of the linear system. We can start with the continuous time linear time varying or LTV system, which is defined by the state equation as in equation number 1, in which t is the continuous time instant, which belongs to the real interval from 0 to tf, where tf is the length of the time horizon. X of t is the state vector in continuous time, which we denote as x, and u of t is the control input vector. A of t and b of t are the system metrics and input metrics respectively, which can change with time. A special case occurs when A of t and b of t are constant matrices that does not change with time. In that case, we call the system as linear time invariant or LTI system and can be represented as in equation number 2. As an example of the continuous time linear system, we consider the first order system defined by equation number 3. In linear state feedback, we select the control input u equal to minus kx, where k is some feedback gain. And by substituting this in the state equation, we obtain the closed loop dynamics as in equation number 4. This is a first order linear differential equation, and from the basic differential calculus, we have the solution x of t equal to e raised to a minus bk t into x of 0, where x of 0 is the initial condition or initial state. Here, a minus bk is a scalar, and the convergence rate of this exponential function depends on the value of a minus bk. Now, as per the control law, we have the control input u of t equal to minus k times x of t, which is equal to minus k into x of 0 e raised to a minus bk t. At t equal to 0, we have e raised to a minus bk t equal to 1. Therefore, the initial value of the control input will be equal to minus k x0. For simulation, we consider a equal to 2, b equal to 1, 3 different values of k, which are 3, 5 and 7. And the initial state is chosen as 5. Now, for k equal to 3, we have a minus bk equal to minus 1. For k equal to 5, it will be minus 3, and for k equal to 7, it is minus 5. Clearly, e raised to minus 5t converges with a faster rate compared to e raised to minus 3t and e raised to minus t. Therefore, for k equal to 7, the response will be faster, and for k equal to 3, the response will be slow. Similarly, for k equal to 3, we have the initial value of the control input is equal to minus k times x0, which is equal to minus 15. And for k equal to 5, it will be minus 25. And for k equal to 7, it is minus 35. Therefore, the initial value of the control input is maximum for k equal to 7 and minimum for k equal to 3. Figure 2 shows the response of the first order system, which shows the plots for the states and the control input. Here we can see that for k equal to 7, the states converge to 0 at a faster rate, and for k equal to 3, the response is very slow. Whereas for k equal to 7, we require a larger control effort during the initial period, and for k equal to 3, the control effort required is less. Next, we move on to the discrete time linear time varying or LTV system, which can be defined by the state equation as in equation number 8. Here, k is the discrete time instant, which belongs to the set of integers from 0 to n minus 1, where n is the length of the time horizon. Sk is the state vector in discrete time, and uk is the control input vector. Ak and bk are the system metrics and input metrics respectively, which changes with the time instant k. Here also, a special case occurs when Ak and Bk are constant matrices. In that case, we call the system as linear time invariant or LTA system, and can be represented as in equation number 9. As an example of the discrete time linear system, we consider the first order system given in equation number 10. Now for the linear state feedback, we have uk equal to minus k times xk, where k is the feedback gain. And by substituting this in the state equation, we obtain the closed loop dynamics as in equation number 11. From this equation, we have x1 equal to a minus bk times x0, x2 equal to a minus bk times x1, which is equal to a minus bk square times x0, and similarly xk equal to a minus bk raised to k times x0. Here a minus bk is a scalar, and the convergence rate of this exponential function depends on the magnitude of a minus bk. Now we have the control input equal to minus k times xk, which is equal to minus k x0 into a minus bk raised to k. At k equal to 0, we have a minus bk raised to k equal to 1. Therefore, the initial value of the control input will be equals minus k times x0. For simulation, we consider a equal to 0.9, b equal to 1, three different values of k, which are 0.3, 0.5 and 0.7, and the initial state is chosen as 5. Here for k equal to 0.7, a minus bk has a smaller magnitude, therefore the convergence will be faster. Whereas for k equal to 0.3, a minus bk is larger, therefore the convergence will be slow. Similarly, for k equal to 0.7, minus kx0 will be larger, therefore the initial value of the control input required will be larger. Figure 3 shows the response of the first order system, which shows the plots for the states and the control input. Here also we can see that for k equal to 0.7, the response is faster, whereas the control input required during the initial period is large. Here we can try with many other values of gains and also time varying gains as well. For each gain, we get a different control signal, corresponding to which we get a different state trajectory. In general, for faster transient performance, we have to use larger control effort in the transient period. Using larger control effort may not be acceptable in many of the cases due to practical limitations and efficiency considerations. Therefore, in practice, we have to select the feedback gain as a trade-off between transient performance and control effort. This leads to the LQR, which gives an optimal way of selecting the feedback gain by considering both the transient performance and control effort. Next, we move on to the LQR and its formulations. LQR is an optimal control approach which results in a linear state feedback control law. One of the major approaches based on linear state feedback is the eigenvalue placement, which is also known as the pole placement. In the eigenvalue placement, the feedback gain k is chosen for placing the eigenvalues of a minus bk at desired locations. The eigenvalues of a minus bk specifies the transient performance. Therefore, in eigenvalue placement, we design the k according to the transient performance. LQR can be considered as an alternative to eigenvalue placement, in which the control law is designed by minimizing a quadratic performance measure, and it results in a linear state feedback. The popularity of LQR is mainly because of the reasons that it considers both the transient performance and control effort in designing the control law, whereas eigenvalue placement mostly based on transient performance requirements. Moreover, LQR can be easily applied to linear time varying systems, whereas eigenvalue placement of linear time varying systems is computationally complex. Next, we move on to the different formulations of LQR problems. Let's start with the continuous time LQR, in which we consider the continuous time LTV system as in equation number 50. The cost function is chosen as a quadratic sum of the states and control inputs as in equation number 16, in which Q is the weighting matrix for the state, R is the weighting matrix for the control input, and QF is the terminal weighting matrix. The weighting matrices Q and R can be used for relatively weighting the contribution of the states and control inputs in the total cost J. If we need faster transient performance, we have to give more weightage to Q, and similarly for lesser control effort, we have to increase R. Q and R are usually chosen as diagonal matrices, and we can add different weightages to the individual elements of the state and control vectors by adjusting the diagonal elements of Q and R suitably. Now, the continuous time LQR problem is to compute the control input for the linear system, which minimizes the quadratic cost. Next, we move on to the discrete time LQR, in which we consider the discrete time LTV system as given in equation number 70. The cost function is chosen as a quadratic sum of the states and control input as in equation number 18, in which Q is the weighting matrix for the state, R is the weighting matrix for the control input, and Qn is the terminal weighting matrix. Here we have a summation instead of the integration, and this is because of the discrete nature of the system. Now in the discrete LQR problem, we have to compute the control input sequence for the linear system, which minimizes the quadratic cost. Next, we move on to the constraint LQR problem, in which we consider the linear system as given in equation number 90. Here the main difference is that the state vector xk and the control input uk belongs to some constraint sets, which we denote by x and u. And the constraint sets for states and control input can be represented using linear inequalities as in equation number 20. For example, in the case of second order systems, the constraint set for the state can be represented as in figure 4. Here we use a set of linear inequalities corresponding to which we have a feasible region as shown in the red color. And this set of linear inequalities can be compactly represented using a matrix inequality like this. And we will discuss this in detail later. Now, the cost function is chosen as in equation number 21, in which Q and R are the weighting matrix for the states and control input, and Qn is the terminal weighting matrix. Now, the constraint LQR problem is to compute the control input for the linear system with the constraints that minimizes this quadratic cost. Here, we formulated the constraint LQR problem for the discrete time linear system, and similarly, we can formulate the problem for continuous time linear systems as well. In the next few lectures, we will be discussing the continuous time LQR problem. Then we move on to the discrete time LQR, and finally constraint LQR. That completes this lecture. Thanks for listening.